All right. Good morning, everybody. Thanks for joining us. We're here in the training room at the headquarters of Promess Incorporated in Brighton, Michigan. Today, we're going to spend about 30 minutes talking about how to solve 4 basic press fit applications. My name is Greg Cooke. I've been an applications engineer with Promess for about 13 years. I'm currently based in Huntsville, Alabama, and I cover the southern United States for Promess. With me today, I have Lee Bertossi.
Hi, everyone. I'm Lee Bertossi. I am the application engineer that resides out of Charlotte, North Carolina for Promess. I've been with Promess about 5.5 years now, working with Greg and the rest of the team. Today, what we're going to talk about, our topic of discussion, is 4 basic press fit strategies that we most commonly come across helping customers assemble their parts. During this webinar, there will be a question and answer sidebar here. Please submit any questions before we conclude this today. We're going to go ahead and do our best to answer them, and we'll go from there.
Before we jump into the applications, we thought it would be helpful for anyone who's not familiar with our systems if we did kind of a brief overview of the system itself. So we have here one of our presses. This is obviously the biggest piece of the system. We have standard press sizes that go anywhere from 0.2 kilonewtons, which is about 45 pounds, up to 1 meganewton, which is 225,000 pounds. All of our presses have equal capacity, tension, and compression, so you can pull with just as much force as you can press with. They're all ball screw, so there's no air, no hydraulics, nothing like that. The silver band at the top here is the load cell. That's where we get our force feedback. We also have a servo motor on the back here with a built-in encoder that gives us our position feedback. We can also take in external sensors. So if you have a pressure sensor, flow sensor, something like that you need to use in your application, we can accommodate that. When you get a press system from us, it will also include a servo amplifier, controller, all the cables, and the software. So with our controller and software, the system will be fully programmable. So you can press to a position and monitor the force. You can press to a force, monitor the position, any combination of those sensors that you have in the system. We also have data collection included with our system. So you can do things like a force versus distance curve. You can collect individual values like peak force, final position, things like that. A typical force versus distance curve will look something like this. So we'll have force on the y-axis, position on the x-axis. You get your curve, and then you can set limits around that curve that you can use as pass-fail criteria. You can also define a window where you're going to check those limits. We call that our monitoring window, so you can really zero in on the part of the curve that you actually care about. So you've got your curve, and like I mentioned, you can also collect the individual values, peak force, final position. Any of those values can also have tolerances set on them.
So a little bit about the application or the press strategies that we're going to discuss today. As I mentioned, there was 4. The first one is pressing to a position. We're also going to cover pressing to a force. The third one will be pressing to an external transducer. And the fourth one will be pressing to relative values. There's 2 ways to accomplish that. But moving forward, the first one that we're going to discuss is pressing to a position. For those of you who are familiar with data collection, this will look familiar. For those of you who aren't, when you press to a position, you might get a curve that looks something like that. So as we contact the part, we are going to build force and hit a final position value. We've done a variety of applications with this, dowel pressing. We've had spring pressing. We've done spring testing to evaluate that, collecting points to validate the spring rate as we're pressing on it. We've pressed bearings onto shafts. We've pressed shafts onto bearings. All types of different applications using this strategy. We've seen this done with other types of technology, but the way that we handle it is a little bit different than what some other systems might do. When pressing to a position with an air cylinder, you would have like a travel limiter. or something of that manner. So it's going to go to a position that has to be mechanically controlled. With our system, we can use the feedback from the encoder to program in a position. And what's really nice about a servo press is you can program multiple positions at multiple speeds. A servo press does feature velocity control, which a lot of people with other types of technology don't really have velocity control, don't know how to utilize it. How we most commonly utilize it, though, is rapiding down to a part at a high rate of speed to reduce cycle time. Then when we're pressing the part, we can do it at a control speed. And again, the velocity control has more effect than you may be familiar with. There's different things that we can do when we're pressing to a position. The most common thing that we're checking is the force that we've reached, typically the peak force, but you can also validate with monitoring windows that Greg said, any force during the curve. So if you get a good part, it would hit these windows and we would be able to pass and fail it immediately. When we run the next part, say there wasn't a part present, we would still go to the same position, but we wouldn't achieve the proper force at the proper positions. And even if you have one that comes through the middle and then maybe the part breaks and the force drops off, we can immediately flag that during the process. Again, that's a lot of what we do. A lot of customers historically, and some even currently, they will press to a position in one station and then they will gauge the part in another station. With our technology, we can assemble and gauge all in the same station, reducing complexity. There's many buzzwords for this, no fault forward. We can immediately flag it as a bad part, eliminating downstream work, which might essentially waste time for you. With this press strategy, we can achieve very fast cycle times because we're telling the press exactly where to go and exactly what speed to get there. I think the fastest application that I've ever done is less than 500 milliseconds. Of course, it depends on how much distance we have to travel, but we'd be happy to discuss your application and even calculate the cycle time since we have that velocity control.
That's part to part cycle time, right? Less than 500 milliseconds part to part.
When the cycle started, we achieved it in 457 milliseconds. Then, of course, they would roll a new part in. Yep.
All right. Next application or next strategy we'll talk about is pressing to a force. This is going to be similar to what Lee talked about with pressing to a position, but instead of moving to a position, you're going to move to a target force. This is going to use closed loop feedback with the load cell in our press. This is going to be useful for applications where you're pressing to a shoulder or a hard stop, things like pressing a bearing into a housing. This is also, when you give it your target force, you're going to be able to measure that final position. What you'll usually see for a curve when you're pressing to a force is something like this, where you'll get to your get to the end. So if you know that your part takes, say, 20 kilonewtons to be fully seated, maybe you tell the press to move to 25. It will move to that 25 kilonewtons every cycle, and you'll make sure that you've got your part seated. So say you're pressing, like I said, a bearing into a housing. I think my drawings get worse and worse every time I do them.
You're a great artist, Greg. Don't worry about it.
So you want this bearing to be fully seated here. Like I said, you know it's going to take 20 kilonewtons to get through here, and once it gets to that shoulder there, you should see that force spike up to 25. That's fine for most of the parts. Say you have a part where maybe the housing is machined too small, so it's just a little bit tighter than it should be. What you would see then on the curve is something like this, where you reach that 25 kilonewtons, but you do it before you should. So like Lee mentioned, we can be gauging that final position, and you can set whatever tolerances you need on that position. So if you get a part that comes in here and it's pressed and it gets the target force too soon, maybe you're 4 or 5 millimeters away from being bottomed out, we can catch that, flag it, and you can pull that out, reject the part so you don't go any farther with it. and assemble something that's not assembled correctly. There actually is an algorithm in our software that will try to decelerate as it approaches that target force. So you should be able to hit that target force very accurately every cycle. One other way we've used this in the past is for pull tests. So I mentioned before that the presses can do equal capacity, tension and compression. So if you have something like a bearing, you press it in. After that, you want to do a pull test on it to make sure that it's not going to fall out. What we've had customers do is build like a gripper into their tooling so they can press the bearing in, maybe flare it out or hold on to the bearing somehow, and then reverse directions and pull. You can do the same thing, give it a target force to pull to, and then gauge that travel or that position. So you can reach that force and then make sure that it hasn't traveled or that it hasn't moved from that final position. So again, you can, if something is not assembled correctly, you can flag that, pull it out so you don't send it down the line to have anything else done to that part.
Yeah, we've seen debris get lodged in under the bearings. Of course, we want to detect that. We've never have any outside debris fall into a part, and cause a downstream failure. But yes, we use this strategy most commonly. I've also seen it, other types of technology, maybe a hydraulic press, where you're using tooling controlled hard stops. So the press comes down and just hits the tooling. Well, there's tooling wear. We don't have that issue because we're not coming down on the tooling and wearing the tooling out. So very, very common press strategy. Now, bear with me, you get to see some of my artwork here in a second. It's a little more complex of a process, but pressing to an external transducer. What that means is using an outside component. We have positional feedback from the motor. We have a load cell that we can take into it. But some processes are more difficult than that. Pressing to the two types of transducers, we have a positional transducer and a force transducer. I'm going to speak about a positional transducer. I've worked on several of these applications. Say we have a surface. Doesn't matter where it is, a bushing or a pin press. And let's say what the design spec calls out for is this pin needs to be pressed to a dimension based off of this height right here. So in this example, we'll say we want this pin to stand proud of this surface by 5 millimeters. So how we would tackle this with an external position transducer is we would have our press ram coming down in this direction, pressing this pin in. And what we would do is we would mount a position transducer off to the side that is reading this surface. So as the press is coming down, this position transducer knows exactly where this press ram is. We can count down 10 millimeters away from target, 9 millimeters away, 5 or 6. And as soon as we hit the target window, we know exactly that we're 5 millimeters proud of this surface. So kind of going back to what I said before, we allow you to assemble and gauge in the same process. As part heights change, as different, maybe a palletized line changes, we can incorporate this press strategy to help you achieve the results that you want without having to use a tooling controlled hard stop, because then you're, again, always worried about the integrity of the tooling. We got to gauge it. We have to change it. There's more time added to the manufacturing process. And we're in manufacturing, we're trying to get the parts out the door, assembled properly. So just a little bit of insight of how we've done that in the past to help our customers achieve the desired results. Now, moving on from external positional transducers, we want to talk about external force transducers. So yes, we do have a force transducer built into the press. What happens if we have a process where we need to gauge both a high force with the internal load cell and a very low, high resolution, high accuracy load cell for another process? One thing comes to mind for me We helped a customer essentially combine two operations into one station using this strategy. We had a press, and what we did is we mounted a very high accuracy load cell to the tip of the press ram. I think it was a 1 kilonewton external ram mounted transducer. And what we would do is we would come down into a connector assembly and insert a pin into a component. And it was very critical that we lock this component in. During that assembly, once we gauged and monitored that force, there was compliance built into the tooling where it would be spring loaded and go into the tooling on the press ram. And then we would go down and crimp the component, and that force was much higher than the 1 kilonewton external load cell. It was more around 10 kilonewtons. So utilizing the internal press load cell, we built a force distance graph for the crimping portion of the process. So again, combining two stations into one, utilizing some of our technology and an external load cell with its own force and position graph, qualifying one process, and an internal load cell, qualifying the second crimping process. So some extra versatility.
The load cell built into the press is usually going to be accurate plus or minus 1% of the full range. So if you have, like a 12 kilonewton press and you need to measure down in that lower, half kilonewton range, whatever it is, if you get down where the force you're measuring is much lighter than the actual press, that's where we would want to use an external load cell, because that external load cell can be calibrated down into that lower range. So you can measure those lower forces accurately, but it can also be mechanically overload protected, so it can take the force of.
Yes. Should have. Good catch, Greg. Thank you very much. That's what 13 years will do as opposed to 5. I forgot one thing. The second time we've used external force transducers is for a more complex process. One thing comes to mind, and it's pressing wheel studs into a wheel hub. If you're familiar with this is what your tire actually bolts to your car. So it's a circular assembly. We need to press in 4 studs on this application. So of course we could press in 4 studs with one press, but the problem is if we were missing one stud, our force distance graph may not show that with only one load cell. So where we helped this customer was we put an external load cell built into the tooling to monitor each stud independently as it was being pressed. We used the feedback from the motor, so we could create 4 force distance graphs for each stud, thus verifying that each stud was pressed independently. We make sure we didn't have a misload. We saved cycle time because we could press 4 at once, and qualify each one as it was going along. We've also used this for staking operations on maybe a planetary carrier, any process where we have multiple components. One other thing that I've seen this used for is prototyping or development stations. They want to have a wide array of capability and utilize one press. It's not in production, but with the accuracy that we offer, we work with a lot of development companies, their R&D labs. And what's really great about that is they can prototype with one of our programs. And then when that design goes into production, it's the same piece of equipment. Everything's already been qualified. We already have the program made in most cases. So we go seamlessly to production. But with these development stations, a customer that I have had a 100 kilonewton press, and then of course was doing some very accurate processing. So they made a quick change coupler. When they need higher accuracy, they can take an external load cell, mount it to the press ram, and it essentially takes a 100 kilonewton press with this external load cell at maybe 1,000 pounds to bring the force readings in and essentially give them the accuracy that they need. We've also done this on tooling shuttles where they maybe have a load cell built into the nest. I've talked a lot about mounting them to the press ram, but you can actually mount them in the nest of the different nesting. So this press that I'm thinking of now has 3 stations. We use the press ram for one, Then as the part shuttles over, we use the load cell, external load cell that's built into the nesting to qualify the next process. I think I covered most of external transducers that we have. Sure, I'm forgetting a couple, but feel free to call us with your application.
All right, the last strategy that we'll talk about today is pressing to a relative value. That could be two different cases, really. The first one would be pressing to a force, like a touch point, then moving a relative distance from there. Or you could also move to a position and move a relative force from there. So first we'll talk about moving to a force, then a relative position. So something like a touch point. Where that's good is for things like a palletized line where the starting height of the parts may vary from part to part. So if you think about something like pressing a pin into an armature, and my armatures are not very uniform, but hopefully you get the idea. So as the armatures are coming into the station, you've got a pin that you're pressing in. The starting height is going to change from part to part. So what we can do then is have our press ram come down, move to a light force. You know, if we say maybe we have a 3 kilonewton press, it takes 2.5 kilonewtons to press these pins in. Maybe we move to something like 100 newtons, something just to let us know that we've contacted that pin. Then we can move a relative distance from there. So after we contact, we want to move 10 millimeters. So every part that comes into the station then will be pressed 10 millimeters from where it starts. So the pins can be in the correct position. You can get good parts out of the station, even though the starting height varies from pallet to pallet or part to part. So that's one example. The next one is if we're going to press to a position and then a relative force. This is going to be good for things like fragile parts or things that can break easily. A lot of times they're expensive. I've worked on, I think the place I've used this the most is with things like pressing connectors onto circuit boards. Obviously, circuit boards can get expensive. You don't want to scrap them. You also don't want to apply too much force for any one part. So you can't necessarily just say press every part to 20 kilonewtons because that might be too much for some parts and might damage them. So what you can do then is what you'll see on, if you look at a curve, is something like this.
Channel that inner Bobby Ross.
Happy little curves. So your final position might be the same for every part. So we'll call that 90 millimeters. In this case, you know, you don't want to go all the way up to a force up here on this part because it doesn't take that much force to assemble that part. It could damage it. You might have to scrap it. So what you can do is move to some position before the final position. You can usually get fairly close. So we'll say something like 87. Get to that 87 millimeters, then move a relative distance or relative force from there. So on this part, say at 87, you're at 5 kilonewtons. And we're going to tell it to move 3 kilonewtons past that. So on this part, we're going to go to 8 kilonewtons. That part's going to be fully seated, fully assembled, not damaged. This next part, you've got 10 kilonewtons when you get to 87 millimeters. We're going to move 3 kilonewtons again. So on that part, it's going to push to 13 kilonewtons. That part also will be fully assembled, not damaged. This last one, maybe we're at 15. So this part, it's going to go up to 18, 3 kilonewtons past your 15. Once again, that part will be fully assembled, not damaged at all. That can vary from part to part based on whatever force that part takes to get to at that position. All right. I think that's all we have for the basic applications. We'll jump into some questions and answers. If you do have any questions that you forget to ask today or that we don't get to, feel free to contact us at Promess 810-229-9334. You can ask for any of our sales or applications engineers, and we'll be able to help answer questions. You can also email us at promess@promessinc.com. go ahead and
Question time.
First question, what is the accuracy of the system? So there's a couple different accuracies we can talk about, I guess. The first is going to be the load cell, so the force accuracy. Kind of the standard number that we use is plus or minus 1% of the full range of the load cell. It's a strain gauge load cell. That's kind of the safe number. A lot of times we can do better than that. Kind of plus minus 0.5% of the full range is more common. Like I said, plus minus 1% is kind of the safe number. Then the positional accuracy, the encoders that we use on our servo motors are going to be accurate plus or minus 25 microns. And that's of the press ram. We can, like Lee talked about,
we like to say repeatability. There's always machine deflection in there. So if you tell the press ram to come here, retract, and come back to that position is where we get the plus minus 25 microns. Most of the time. There's a difference between accuracy and repeatability, but yes, we can use external transducers. And I think the closest standard deviation I have ever achieved with a customer was a 100-part lot, and they were within 0.8 of a micron using some digital probes. So some very high accuracy digital probes. They're plus minus 0.5 of a micron, and of course, standard deviation is how quickly or how closely can we repeat a result for the customer.
All right. Does the system record the graphs we talked about?
Want me to handle that one?
Go for it.
Yes. So onboard storage can be utilized. There's many different ways to store data, traceability, Industry 4.0. You can call it whatever you want, but in standard format, we do store all of these curves, if you want to, on our proprietary controller. That is all built into the controller. If you want to store them on a PC, our controller can onboard them to a station PC if it's acceptable for that. If you don't want to use a station PC, but you still want to bring that data back into a server, of course, traceability now, we do offer a software package called the Promess Data Service that allows multiple controllers to store all of the data to a central location. We can convert them into pretty much any format you would like. In standard, we stored it in an SQL format, but we'd love to handle your questions and talk more about that. But those are conversations that can take a little while.
How would we determine if a bearing was placed at an angle? Also, how would we design the preload to constant force and determine the shoulder has been reached? So how would we determine if the bearing was placed at an angle? A lot of times what you'll see for something like that is you'll get, so maybe a normal curve looks something like this. If you have the bearing placed at an angle, you might see a higher spike in the beginning here, and then maybe a drop off as it kind of corrects itself and jumps into place. So usually you'll see some anomaly like that on the curve. And I mentioned that we can set curve limits earlier. So most of the time you can catch something like that with your curve limits. You can also do things programmatically where you're, maybe you're grabbing the force at different positions. You can calculate differences between forces at different points. Usually the best way to handle something like that is during the setup phase of the machine, you try and kind of force those conditions and see what the data looks like. And then you can design a strategy around what that curve for that specific part looks like.
One thing that I've seen in the field about these different anomalies that you'll have is when you get your standard press curve, looks something like that. If the bearing's cocked at an angle, you'll actually run into that bearing earlier than you would if it was sitting flat. So one thing we mentioned we grab final position. We also talked a little bit about a touch point. So we can always record these forces. And one thing that I've done is we have an internal math engine in our software. We can calculate how long we were in contact with a bearing. So if we know it's a 10 millimeter bearing getting pressed into a 10 millimeter pocket, we better see contact force for at least 10 millimeters or something's wrong. If the bearing's cocked, you might get something like this. And we can say, well, that was 12 millimeters that time. What happened? Maybe we flagged that for a bad part. Maybe we don't. It's all dependent on what you want to do.
Calculate that interference distance and then set a tolerance on it.
Mm-hmm. I've used that quite a bit.
Okay.
Ed, was there something about verifying that we bottomed out on that last one? Also, how would you design the preloaded constant force to determine the shoulder's been reached? What I've done with this sounds like this. They're asking, how do we confirm that we did bottom out? Kind of the same way we do final position and touch point. I've done force deltas. So we can collect a peak force value. We told the press to go to, let's say, 20 kilonewtons. We can also go back and record, we typically call this bottom out force or press force internally, but we can do the same thing here where we calculate the press force, we calculate the peak force to determine this delta and make sure that the part was in fact seated with enough press force. Some customers do more complex things with that, but I think we're going to save that for the next webinar.
We're going to talk about recommended tolerances to have between matching parts to achieve ideal press fit conditions.
What was that one again? Are we going to talk about recommended tolerances to have between matching parts to achieve? Oh, I think they're maybe referring to our taut curve where we help customers clone the perfect part. So what we do when we're running parts is we store the curves as we talked about. And what we typically tell customers is to find 5 or 10 perfect parts. Have your gauging department, your quality department gauge them, make sure we have a nominal OD and a nominal ID for their parts. And we'll run those curves. And they're going to vary a little bit. But one of the functions with our software is to have a taut curve. So what we do is we record all of these force curves. And then we come back and we average those curves together for kind of a master curve. So what we would, and it shows up in green in our software, that's why I chose green, but we'll take a master curve and then we give you the ability to apply relative limits. Typically we use plus minus 10% of our nominal curve. But again, we can apply these relative limits throughout the whole curve. And if, as Greg mentioned earlier, we can use a monitoring window to draw in on a certain area of the curve to apply those limits. So that now we have a taut curve based on your nominal parts, and we're going to qualify them plus minus 10%. You can adjust those limits to 5%, 20%, whatever you feel, or maybe we don't even use the upper relative curve. Maybe it's just a relative lower curve. So I hope that answered that question.
That can also be, you mentioned finding, 5 or 10 nominal parts. That doesn't have to be parts that you know are good ahead of time. You can also take, you can look back through parts that you've run in the past and pick out 5 or 10. Mm-hmm. You say, okay, these 5 or 10 are the good parts that I want to use as my nominal curves or as my taut curve. You can use those curves after the fact to generate your taut curve and your limits. Right. So to define the force to assemble a part, I need to send you some samples. Yes, you definitely can do that. We have our process development center here. So if you're not sure how much force your application will take, if you send us some parts and then any special tooling that we would need, we can actually set up some development work here in our process development center where we actually press the parts together. We can collect the data, generate the data, send that back to you with the parts so you can kind of see exactly what the capabilities are, how much force it takes, what size press you need, all those types of things. And you can also feel free to join the parts here in the Process Development Center, so you can be here with the parts to be part of the development and see everything kind of as it comes together.
Yep, we'd be happy to host you. It's very intuitive for our customers to really see how the process is developed, especially moving from maybe not a servo press into the servo press world. It might be a little bit more than you think, but you supply the parts and we'll supply the engineer to program it and all the equipment so that you can take the data back to help build your case as why we need this to help us build better parts.
And that's typically, we provide that at no cost.
Certainly.
So that's something you can get a good idea of the capabilities and equipment sizing and everything before you have to spend any money on the system. Is servo press working in torque mode when pressing to a force? Typically, no. We have done that in the past, but for the most part, it's much more accurate and more reliable to use the closed loop feedback directly from the load cell. So we're actually measuring, I mentioned earlier, I think that the presses are ball screw. So the ball screw actually runs kind of through the ram, up through the center of the housing, directly through the load cell. So whatever force you're putting on the ram or the ram is applying to your part is being transmitted directly through that load cell. So we're measuring the force directly on the part without having to calculate it or rely on, a motor torque or anything like that.
Yes, it's quite a difference. I've had a couple customers that were going from a motor torque scenario to our closed loop feedback, and world of difference on the results they were getting.
Wondering what influence surface finish versus size can have on a press application.
Quite a bit in my experience. We've actually helped some customers do this, and I think a lot of it pertains to the velocity control that we offer with our units. So you can see different things. One thing that we've encountered in the past is a very rough surface finish building force. We've seen that and it depends on your parts, of course. Every scenario is different, but typically, if we were pressing this at 5 millimeters a second, and then we sped that up to 8 or 10 millimeters a second, we would see less jaggedy peaks, and the force typically reduces when you press it faster. That's some things that I've experienced. Greg, do you have anything to add to that?
Yeah. So like Lee said, the surface finish can have quite a bit of impact. I've seen it most often on equipment sizing, really. I've had customers that would size equipment, maybe buy a 60 kilonewton press because they're pressing bushings in or whatever the case may be, and then somewhere down the road they start putting oil on the bushings as they're inserting them. A lot of times that may cut the force in half. It's obviously specific to each application, but that's one of the things with the Process Development Center. We can test for ahead of time, and ideally when we do the development work here, we're going to be as close to a production environment or production conditions for the parts as we can be.
Yeah.
That can help get us a pretty good idea how much force it will take and what you'll see in production.
Yeah, I mean, whoever brought that question, please come visit us in the PDC. As Greg mentioned, we both take turns on the pager. One thing with Promess is 24/7, 365, no cost phone support. I've gotten a call. I think it was about 2:30 in the morning. Yeah. Our press forces are crazy high. And one of the questions I asked was, do you oil these parts? And come to find out there was no more oil in the oil system, or it was plugged, something happened to it. So you will see quite a bit of difference. So come to our PDC. We're happy to go over your exact process with your exact parts and try to come to all the conclusions to help develop it.
All right.
I think we ran out of questions here, or maybe our answers are just that good. But thanks for attending our webinar today. I hope this gave you a little insight on the 4 most common press fit applications that we have. Coming up in the future, we're going to unlock the full capabilities of a servo press and go into some more advanced strategies. So if we didn't cover your application today, please stay tuned.
If you do have any questions we didn't get to today, or if you think of something down the road, feel free to give us a call. Phone number here is 810-229-9334. Or you can also email us at promessinc.com. Thanks, everybody.